Welcome to this explainer. Okay, so have you ever felt like the universe is playing by a set of rules nobody bothered to hand you? Kind of like there's this secret operating system running quietly in the background of your everyday life? Well, today we're going to dive right into that invisible rulebook, the one that governs literally every single movement in our universe. We're going to take those massive, complex mathematical formulas you might have stared at blankly on a chalkboard and translate them directly into things you physically experience every single day. Think of this as finally discovering the master code for exactly how our physical world operates.
But before we even touch the math, I want you to tap into your own physical memory for a second. Think about it. Why is it that when you're standing on a moving bus and it suddenly slams on the brakes, your body violently lurches forward and you have to desperately grab a handrail to save yourself? Or, on a slightly more mundane note, why does a heavily loaded shopping cart stubbornly fight you when you try to turn it down the cereal aisle? Look, these aren't just random annoyances or, bad wheels on a cart. They're actually profound, invisible physical laws at work, dictating absolutely everything you do.
So here is our roadmap for today's explainer. First, we'll uncover the universe's invisible rulebook. Then we'll look at inertia and why resisting change is such a struggle. After that, we'll dive into force, mass, and momentum, followed by reactions, friction, and curves. And finally, we'll wrap up by showing how mastering this physics blueprint is your ultimate key to acing exams.
All right, let's jump right into Section 1, the universe's invisible rulebook. Let's look at the grand design of our physical world.
It's incredibly easy to look at the world around us and just see total randomness. But honestly, the universe isn't chaotic at all. Every single action follows a highly specific, totally predictable set of instructions. Whether you're dribbling a basketball and feeling the exact fraction of a second it bounces back into your hand, or you're a carpenter tapping a hammer to wedge a heavy metal head tightly onto a wooden handle, or even just watching a bird flap its wings to stay airborne, absolutely everything is following the laws. By observing these laws of motion, we can predict exactly how objects will behave before we even lay a finger on them. It's the whole reason we can predict a total solar eclipse decades in advance, or calculate the exact trajectory to land a rover on Mars. It's this unbreakable connection between the stuff we touch and the forces that act on them.
Since we know these rules exist all around us, let's move to Section 2, inertia, and examine how objects stubbornly, aggressively resist change. Let's look at two sides of the exact same phenomenon. First up, the inertia of rest. You've probably seen that classic parlor trick where heavy coin sits on a playing card over a glass. If you flick the card away fast enough, the coin doesn't go flying off with the card, it drops straight down into the glass. Why? Because an object at rest desperately wants to stay at rest. But on the flip side, we have the inertia of motion. Think back to that bus analogy we talked about. When a moving car stops suddenly, your body has this really powerful tendency to continue in its state of uniform motion. Basically, your body wants to keep doing exactly whatever it was just doing. This exact concept, objects in motion aggressively wanting to keep moving, is the literal reason safety engineers invented seatbelts. They're designed to completely counteract your body's dangerous desire to keep traveling at the speed of a crashing car.
Okay, so we've covered why objects resist change. Now let's introduce the actual math behind forcing an object to change its state in Section 3, force, mass, and momentum.
Picture this. You're back at the supermarket. When you push a completely empty shopping cart, it's an absolute breeze, right? You can steer that thing with one finger. But as you pile it high with heavy groceries, gallons of milk, canned goods, you physically feel a massive difference. You have to push so much harder just to achieve the exact same walking speed. In that very moment, you aren't just doing Sunday chores. You are literally experiencing Newton's second law. The mass of the cart went up, so the force required to accelerate it has to increase proportionally. It's that simple.
And this brilliantly illustrates the translation from a physical feeling you have every single day to a rigorous mathematical formula. Pushing a heavy school bag versus an empty one, that's a direct application of force equals mass times acceleration. And that isn't just a textbook formula. It's the exact math mechanical engineers use to figure out how much engine power a specific vehicle needs to merge onto the highway. Also consider this. A massive truck moving at a slow crawl can be just as difficult to stop as a tiny sports car moving incredibly fast. That's linear momentum, mass times velocity. Engineers rely heavily on this exact momentum calculation when designing public security barriers meant to stop heavy moving vehicles right in their tracks.
So, here is a massive takeaway. If you want to reduce an impact force, you literally have to manipulate time. Think of a fielder catching a blistering fast cricket ball or baseball. If they keep their hands completely stiff, that impact is going to hurt. Well, it's going to hurt a lot.
Instead, they pull the hands back as the ball enters their glove. Or think of a high jumper landing in a deep, soft sand pit rather than on solid concrete. What they're doing is actively increasing the time it takes for their moving body to stop. This concept is called impulse. It's the change in momentum derived as force multiplied by the change in time.
Now, let's look at how manipulating time actually saves lives. By increasing the time it takes for a high-speed collision to happen, the blunt force of the impact is drastically reduced. That slight, highly engineered delay, literally just tiny milliseconds, is exactly how car airbags work. By inflating instantly and letting your body slowly compress into them, they stretch out the time of your deceleration. And by stretching out that time, they drastically reduce the deadly physical force your delicate body would otherwise absorb from the steering wheel. It's honestly brilliant.
All right, let's keep this moving. Section 4, reactions, friction, and curves. Let's see what happens when forces react against each other, rub together, or spin in circles.
I mean, you can't really talk about physics without bringing up rockets, right? Let's break down Newton's third law and the conservation of linear momentum. Step 1. A rocket engine ignites and violently ejects massive amounts of exhaust gases backward at terrifying speeds. Step 2. Because linear momentum must be perfectly conserved in this entire system, Step 3 naturally has to follow. The rocket has absolutely no choice but to experience an equal forward reaction. It literally travels into the vacuum of space by throwing mass backward to propel itself forward. It's the exact same reason a rower pulls heavy water backward with their oars to push a sleek wooden boat forward. Same exact rulebook. Let's connect a few more very familiar sensations to the formulas engineers use every single day. First, when a cyclist speeds into a turn and leans heavily inward, that's centripetal force at play. Civil engineers use that exact formula to bank or tilt our highway off-ramps so our cars don't skid off into the ditch. Next, how about when an elevator starts moving down quickly and your stomach suddenly drops? You know that feeling, right? That's your apparent weight changing, a totally vital calculation for designing safe, comfortable elevators in massive skyscrapers. Finally, think about static friction. Why is it so much harder to start pushing a heavy wooden trunk than it is to keep it sliding once it's already moving? It's because static friction is greater than kinetic friction. That's the whole reason we stick those little felt pads under our heavy household furniture, to reduce the coefficient of friction and save our hardwood floors.
Which brings us to our final stop today. Section 5, Mastering the Physics Blueprint, and how this opens up incredible opportunities.
If you're a student currently studying this stuff, listen up, because this is a real game changer. Highly competitive exams don't just want you to memorize textbook definitions and spit them back out. The true secret to solving those nightmare mechanics problems, whether it's complex tension in a system of pulleys or calculating wild projectile arcs, is developing the intuition to see a physical situation and immediately translate it into a structured mathematical framework. It all starts by looking right past the clutter of the problem and recognizing the core truth: the net force equals mass times acceleration. Because when you master these foundational laws of motion, you're doing way more than just preparing to dominate incredibly competitive entrance exams like the IIT JEE, NEET, or BITSAT. You are actively building your future toolkit. These underlying principles are exactly how civil engineers calculate structural integrity, keeping massive steel bridges from collapsing under terrifying wind forces. It's how biomechanics experts design incredibly advanced medical prosthetics that flawlessly mimic human movement. These rules are the absolute backbone of modern robotics and the very core of designing cutting-edge propulsion systems in aerospace engineering.
Throughout this explainer today, we've touched on 10 super common everyday experiences. From the simple act of beating the dust out of a carpet and the sudden lurching stop of a city bus, all the way to a sprinter exploding off the starting blocks and the sheer, awe-inspiring thrust of a jet engine. These everyday things prove one very important point. You already understand physics intuitively through the movement of your own body. You've literally been living it your whole life. You just needed to connect the physical feeling to the mathematical framework.
So, I'll leave you with this final thought. You now possess the fundamental alphabet of the language of our universe. You truly understand inertia, force, momentum, and reaction on both a physical and a mathematical level. So, now that you have the vocabulary for the invisible rules of the game, what grand scientific challenge will you solve next? Thanks for joining me on this explainer. Keep your eyes open and keep observing the amazing physical world around you.